All right, in this next lesson, I'm going to show you how to write and balance complex redox equations. So what we've done so far, I guess we can call simple redox equations. So these, as we'll see here, are quite a bit more extensive in terms of what we need to do to balance the equation. So some things to remember, same as always, when you're balancing an equation for a redox reaction, both mass and charge must be balanced. And by balance, we mean mass must be conserved. So law of conservation of mass, what you end up with has to have the same mass as what you started with. Charge must balance as well. You cannot have an excess or deficiency in charge. So that must be conserved as well. So here are the rules, or these are more probably steps for balancing complex redox equations. First step is to identify the substance being oxidized and the substance being reduced. And we can do so by looking at the oxidation number. So look at the oxidation number of a substance in the reactants versus that same substance in the products and see if its oxidation state is increasing or decreasing, and that will tell you if the substance is being oxidized or reduced. And this step is important for one of the last steps, as we'll get to in just a bit. So identify those substances and then separate that equation into two half reactions. Should be noted that usually for this class, the substances being oxidized and reduced are substances other than hydrogen or oxygen. It's not that hydrogen cannot be oxidized or reduced, or oxygen cannot be oxidized or reduced. That's not true, but it's just for this class. It's going to be something else that is undergoing the reaction. Next, we're going to balance mass. So step number 2, balance mass. Balance the number of atoms of the element whose oxidation state is changing. Continuing with balancing mass, number 3, here's where it gets a little bit tricky. Balance the number of oxygen atoms, not by adding O, not O2, not O minus 2, but by adding water. Remember that these redox reactions occur in aqueous solution, so there is water present, and so we're going to balance the oxygens by adding waters. Should be noted also that you need to add 1 water per oxygen that you need to balance. That's important for number 4. Continuing on with balancing mass is to balance the number of hydrogen atoms, not by adding H or H2, but by adding H+. Now this is if we assume that the solution is acidic, so many redox reactions occur in acidic solution, and because of that there are H+ ions, and so we can balance the number of hydrogen atoms by adding H+. Now be careful, there are 2 hydrogens per water that you added in step number 3, but 1 oxygen per water, but 2 hydrogens per water, so be careful with that. Next step, and this is where most students make mistakes. They balance mass, okay, it's balancing charge. And so you're going to balance charge by adding electrons to the appropriate side. Now here's where step 1 is important. If you know what substance is being oxidized and what substance is being reduced, then you will be able to easily determine which side of the half reaction the electrons go on. So when something is being oxidized, the electrons that are being lost go on the right side of the equation. When something is reduced, the electrons being gained go on the left side of the equation. So that can at least confirm that you have the electrons on the correct side. Now remember, cannot have something being oxidized without something else being reduced. And so we need electrons on opposite sides of our 2 half reactions. All right, next step is to combine our half reactions to get the overall equations. So of course we're going to multiply one or both half reactions as necessary so that the electrons cancel out. Let's not do step number 7 yet. Let's skip that for a second. Next step after you've combined your half reactions is to check. Again, this is one of the few instances in this course where you will know by your answer if you did it right or not. If mass and charge is not one or the other, if mass and charge are balanced, they're the same on both sides, then you know that the equation is balanced. If one of those is off, guess what? it's not balanced and you did something wrong. My advice to you, in the event that you get to the step and you see, uh-oh, something's not balanced, either mass is not balanced or charge is not balanced, you're going to see in a second that this process is rather messy. And so instead of trying to find your mistake, I would just start over. Now, I got a better solution for you. Don't mess up. Be careful. Go through the steps. Pay attention to what you're doing and do it right once. In the unfortunate event, though, that you do not do it right, start over. That's probably going to be faster and easier for you to get the right answer. All right, step number 7 is in the events that the reaction occurs in a basic solution. So the problem will tell you one way or another if the reaction occurs in an acidic solution or in a basic solution. So if the reaction occurs in a basic solution, you're going to do everything that we just outlined. You're going to pretend for a moment that the reaction occurs in an acidic solution, and then we have some additional steps that we'll do if it's in a basic solution. Here's how it goes. There's different methods for doing this. I think this is the easiest. You're going to add the same number of OH minus ions as there is H plus in your equation. Here's the important thing, to both sides. So let's say you have 5 H pluses on the left. You're going to add 5 OH minuses to both sides of that half reaction, or both sides of the equation rather. It's not going to be in your half reactions, it'll be in the overall balance equation. Now, the side that has both H plus and OH minus on it, so you have 5 H plus and 5 OH minuses on the left side, you're going to combine those to make water. So 5 H pluses and 5 OH minuses will make 5 waters. Inevitably, then, you're going to have waters on both sides of the equation. You can't have that. Can't have the same exact thing on both sides of the equation. So cancel any extra waters that appear. And that is it. Once again, you can check your mass and charge, and if those are balanced, then you are good. All right, let's take a look at some examples. I'm going to sort of use the examples from the book. I'm going to start off, though, with number 26, and I'm going to write it a little bit different than what's shown in your book. So let me write that down and see what we have to start with. Now, how does this compare to the example in the book, number 26? Well, in the example in the book, first of all, we're given an unbalanced equation, it's a net ionic equation. We're given H plus in the equation, which tells us the reaction occurs in an acidic solution. We're also given water in the products. So we can ignore any H plus, OH minus, or H2Os in the unbalanced equation because we'll take care of those when we balance. So I'm just going to get to the essentials, and we have dichromate, iodide. Those react to produce chromium-3 and iodine. All right, so let's do this. Let's identify the substance being oxidized and the substance being reduced. It's not oxygen, so chromium must be involved in the reaction, and iodine. So questions for you. What is the oxidation state of chromium in dichromate? What is the oxidation state of iodine in I minus? And what are the oxidation states of our products? Go ahead and pause the video and come up with those values. So hopefully you got that chromium. Each one has an oxidation state of +6. So chromium is going from +6 to +3. Its oxidation state is going down. That's because the chromium is being reduced. Iodine is going from -1 to 0. Its oxidation state is going up, indicating that iodide, I minus, is being oxidized. So that, again, will help us when we get to the step where we balance charge by adding electrons. All right, next step is to separate into two half reactions. So we want one that has chromium on both sides and one that has iodine on both sides. Now, I chose this one to do first over number 25, as we'll see why in just a bit. All right, step 1, balance the atoms of the element whose oxidation state is changing. That happens to be chromium. This is a common mistake where students will automatically start balancing oxygen. We want to balance chromium, so let's put a 2 there. Next step is to balance oxygen. So how many oxygens on the left? We have 7 oxygens. We're going to balance oxygen by adding water. So how many waters are we going to put on the right side? 1 water per oxygen that we're going to balance. So that's 7 waters on the right. Next, we want to balance hydrogen. So we now have 14 hydrogens on the right. And we're going to balance hydrogen by adding H plus. 14 H pluses, not 7 H pluses, 14 H pluses. All right, now let's balance charge. And to balance charge, what we need to look at is the total charge of everything on the left compared to the total charge of everything on the right. So go ahead once again and determine the total charge of everything on the left and compare it to the total charge on the right. Go ahead and pause and do that now. All right, so we should get a total charge of plus 12 on the left. So this is not plus 1. Common mistake. Some of you put -1 for the total charge. It's not 1 hydrogen, we have 14 hydrogens. That's 14 plus 14. So plus 14 plus -2 is positive 12. On the right side, 2 times plus 3, that's plus 6. Water has no charge, that's 0. So we have a total charge of plus 6 on the right. So what is the difference in charge? The difference in charge is 6, and that will tell us how many electrons we need to balance the charge. Now, which side are the electrons going to go on? Well, let's go back to that first step. What did we say was happening to the chromium? We said the chromium was being reduced. Where do the electrons go in a reduction half reaction? They are going to go on the left side. So adding 6 electrons to the left will balance our charge. If you're unsure of this, check and see, and you'll see that it is balanced. Something else we can do as well is we're going to put the electrons on the more positive side. We have plus 12 on the left, plus 6 on the right, so we'll put the electrons on the left side. So that one's done. And then we go to the next half reaction. All right, next one. This one's a lot easier to balance. Why? Well, we have no oxygens to deal with, so we don't have to add any waters, we don't have to add any H pluses, so this one is pretty easy. So we have 1 iodine on the left, 2 on the right, so we want to balance that. Next, balance charge. So we're already balanced mass, let's balance charge. We said the I minus was being oxidized, so that tells us that the electrons go on the right side. So let's see, we got a total of -2 charge on the left, 0 on the right. So what is the difference in charge? That would be 2. So 2 electrons on the right side. Next step is we want to make sure the electrons gained and lost are the same. So I don't like doing this. Sometimes you'll see that where put the multiplier, the multiple outside the equation. Too many things to lose track of. So I like to change each coefficient. So let's see if I can go back and get rid of those parentheses. So I'm going to multiply everything by 3. So this becomes a 6. This becomes a 3. This becomes a 6. 6 electrons gained, 6 electrons lost. We're good there. Bring everything down that is not crossed off. 14 H pluses, 1 Cr2O7 -2, 6 I minus, 2 Cr plus 3, 7 H2O, and 3 I2. Next step, students like to skip this step. I don't know why. Check. Check mass, check charge. Go ahead and pause the video and do that, and I'll walk you through that in case you need help. All right, so let's start with mass. How many hydrogens on the left? That would be 14. On the right, 14. So far, so good. Chromiums on the left, 2. Chromiums on the right, 2. Oxygens on the left, 7. Oxygens on the right, 7. Iodines on the left, 6. Iodines on the right, 6. Don't assume that just because mass is charged that, mass is balanced, that charge is also balanced. So let's check. What is the total charge of everything on the left side? Go ahead and pause and add that up. So we have 14 plus -2, that's positive 12, plus -6. We have a total charge of plus 6 on the left. On the right side, 2 times plus 3, plus 0, plus 0, plus 6 on the right. mass and charge are balanced. Voila, this equation is balanced. All right, so let's take a look at 25. Again, I'm going to write it a little bit different than what's shown in the book. So let's do that. We have permanganate. And it reacts with H2SO3. And we make manganese 2 and bisulfite, that is called. Sorry, bisulfate, that is called. Again, I'm going to ignore the H plus and the H2O. We'll take care of those when we balance. So this reaction occurs in an acidic solution. This one's a little tougher than the last one because both of your half reactions have oxygen. So you're going to need to add waters to both, add H pluses to both, and you're going to end up with H pluses on both sides. Cancel any extras. You're going to end up with waters on both sides. Cancel any extras. All right, go ahead and pause the video and balance this equation. All right, see if your half reactions match with mine. So I had to multiply the top half reaction by 2, so I had 5 electrons gained, and the bottom half reaction by 5, because I had 2 electrons lost to get these values. Now be careful, we had H2SO3, HSO4 minus, balance oxygen. We have 4 oxygens on the right, 3 on the left, so that's why I added 1 water to the left. And then we had 1, 2, 3, 4 hydrogens on the left, 1 on the right. So that's why I added initially the 3 H pluses. All right, notice that we have 16 H pluses on the left and 15 on the right. So all 15 of these are going to cancel with 15 of those. They're going to be left with just 1 H plus. Likewise, we have waters. We have 5 waters on the left, 8 on the right. So those 5 waters will cancel with 5 of these, and we're left with 3 waters. Bring everything down that's not crossed off. So we have H plus, just one of them, 2 MnO4 minus, 5 H2SO3, 2 Mn plus 2s, 3 H2O, and 5 HSO4 minuses. Equation is balanced. If you don't believe me, which you should not believe me, check. Check and you'll see it is good. All right, let's try one more. This one I don't think is in the book, so let's do this. We'll use permanganate again. I think we can do this one. In an acidic solution, permanganate reduces to Mn plus 2. In a basic solution, let's show that here, you produce not Mn plus 2, but MnO2, manganese 4 oxide. All right, so let's do this. Why don't you balance it as if the reaction occurred in an acidic solution, so just pretend. Just get to that point, and then I'll show you what to do, additional steps to balance, because this is in a basic solution. So go ahead and pause that, balance this equation. All right, if this reaction occurred in an acidic solution, we would be done. But this reaction occurs in a basic solution, so we're going to go back to step number 7. And what it says is we're going to add OH minuses, the ion that makes the solution basic. So you're going to add the same number of OH minuses as there are H pluses to where? That's right, both sides. So I'm out of room on the screen, so I'm going to do plus 8 OH minus on the left, plus 8 OH minus on the right. Now, 8 H pluses and 8 OH minuses make 8 waters. Well, we have waters on both sides. We have 8 waters on the left and 4 on the right. So these 4 are going to cancel with 4 of these, and we're left with 4 H2O. So 4 H2O plus 2MnO4 minus plus 6Br minus makes 2MnO2 plus 3Br2 plus 8OH minus. And there you have it. That's how we balance complex redox equations. It's the same process every time. I know it seems like a lot, but with practice, this is going to become very easy for you. It is a little time consuming when you're first learning how to do this. Follow the steps, get used to the pattern, and be careful with each of those steps. We can do more examples, but I think we will save those for class time. All right, that concludes this lesson. Thanks for watching.